Welcome back, students. This is the session 6 from the chapter of current electricity. The topic is conductivity of a conductor, and here we will be deriving an equation of conductivity of a conductor in terms of the relaxation time. So here I have drawn one figure here. This is a metallic conductor which is placed in an external field. The direction of this external field is indicated by this arrow. Now, in the previous session, we have seen that the direction of the drift velocity is opposite to the direction of the electric field. So, the direction of the drift velocity of electron will be in this direction as given by this arrow. Now, here I have considered one conductor having a cross-sectional area of A, and in this conductor, the current which is flowing in this conductor is I. The current in the conductor is I. Current flowing in the conductor is taken as I. Second thing, the number of electrons per unit volume has been taken as small n. Now, in this figure, I have taken one portion of a conductor as shown by these slanted lines. So, here I have considered the drift of electron through this portion of the conductor in a very small time, say delta t. Now, when the electrons are transported through this portion of the conductor in time delta t, then the length of this portion will be equal to Vd into delta t, because Vd is the drift velocity of the electron and delta t is the time taken by by the electrons to pass through this portion of the conductor. So the length of this portion of the conductor will be equal to Vd into delta t, and the volume of this portion of the conductor will be equal to A, that is the area of cross section, into the length, which is equal to Vd into delta t. Okay. Now, since the number of electrons per unit volume is given as n, or it has been taken as n, so the total electrons which will be transported through this portion of the conductor is equal to n. N is the number of electrons per unit volume, and this is the volume of this portion of the conductor. So n multiplied by this V, which is equal to n A Vd delta t. Now this is the so the total number of electrons which will get transported through this portion of the conductor in time delta t is equal to n A Vd delta t, and the total charge which will be transported through this portion will be equal to, that is this multiplied by E, that is E n A V d delta t, where E is the charge of the electron. Okay, so this is the number of electrons and this is the total charge which is transported through this portion of the conductor, that is this will be equal to the total number of electrons multiplied by the charge of the electron. So this is equal to E n A V d delta t. Now here I have taken the current which is flowing in the conductor as I. So the charge will be equal to I delta t. So now what I will be doing is, I will be equating these two equations, that is this one and this one, and I delta t will be equal to E n A V d dot delta t. So from here I am getting that I is equal to E n A V d, because delta t and delta t will get cancelled out. Now we also know that the drift velocity of the electron, as we have studied in the previous session, that is in the session number 5, that this was equal to E E is the charge of the electron, capital E is the intensity of the electric field, m is the mass of the electron into the relaxation time, which is called tau. So this is the value of the drift velocity. So we can also substitute this value in this equation. So what I will be getting is I is equal to E N A. Now Vd is equal to what? E. This is equal to E upon m tau. So this is equal to I is equal to E square dot N dot A dot E into tau divided by m. E square N E square N A N A E tau divided by m. Okay. Now I will be taking this A on the left hand side of this equation. So this will be equal to I upon A. And I will be getting as E square N E tau divided by m. Now I upon A is what? This was the current density as we have studied in the previous session. So I upon A is the current density. So this is denoted by J. So I will be writing it as this is equal to now J. So yes. So J is equal to E square dot N E tau. Upon n. Now, in the previous session, we have also seen that this E was also equal to J divided by sigma, where sigma is the conductivity of a conductor, J is the current density, and E is the intensity of the electric field. So this was the relation which we have studied in the last session also. So I will be doing is I will be using this equation in order to find a relation between this conductivity in terms of this relaxation time. So now E is equal to J upon sigma. So I will be now substituting the value as N. E is equal to J upon, this is sigma. Okay. So now from here this J and J will get cancelled out. So it implies that m sigma is equal to E square dot N into tau. So it implies that the conductivity of a conductor can also be written as E square dot N upon m into tau. So this is an important relation, and I think everyone should be knowing about this relation also. But this is an important relation, and this is the relation between the conductivity of a conductor in terms of this relaxation time. And so now, summing up, we have got a few important relations which I just want to write it here now. The first one is the drift velocity is equal to E E divided by m into tau. The current density J is equal to I upon A. Then third is the intensity of the electric field is also given by J upon sigma, where sigma is the conductivity of a conductor, and this, that is conductivity, is also given by E square dot N dot tau, which is the relaxation time, divided by m. So these are the four important equations which we have studied in this session right now, and these are the four equations which you all have to remember, because all these equations will be used in solving the numerical problems which I will be discussing in the forthcoming sessions. So till then, have a nice day. Bye.